Thank you very much. So I am very happy to talk in this conference. 2 years ago, I came for the first time, and last year I couldn't come because I was so busy on the way to move from United States to here. And I'm now very happy to talk as a local person. So my title, Open Closed Map, Functoriality of Open Closed Map, looks a bit special. Maybe it is more suitable for a seminar talk, but I plan to talk more about the background of this particular things. And I want to make this title because I want to talk something I am doing recently or now. But most of the talk are somehow background of the whole thing, so which occupies everything about the category kind of things. So since I talk about functoriality, so the one of the motivation of this kind of work is to I want to make this Gromov-Witten maybe Freire theory to be functorial. So something people know that there is something called a quantum cohomology. Quantum cohomology, which associate X to some ring, which is a deformation of the ordinary ring, ordinary cohomology ring, and this is not functorial. I think this is one of the weak point of this Gromov-Witten theory, because the fact that the cohomology ring is a functor is very useful in cohomology theory. For example, if you are algebraic geometer, you want to think that if you have a holomorphic map in a complex manifold, then you can ask whether this guy induces ring homomorphism. And this is not true. So you don't have enough functoriality for the quantum homology. And one nice thing is that the Freire homology, Lagrangian Freire theory, is more functorial. So what it means that following thing. So let X be a symplectic manifold. Then we consider some kind of category. Let's write it f of x. I'll explain more details soon, but this is a infinity category. Then this one is a functorial. So what it means? So you have so I want to say, so to say something is functorial, so we need to say what is a morphism. So you have some morphism from x to y, and this morphism is called a Lagrangian correspondence. So it is something like some manifold of minus x cross y. So minus x means that so it is a kind of pullback of the symplectic form of x minus plus pullback of symplectic form of y. So symplectic form is close to form whose nth power is top form. So this is regarded to be a morphism of this world of symplectic geometry, and the fact that should be the morphism is first proposed by Weinstein. So what it implies the following thing. So you have this functor. We need some condition that's something called unobstructedness, but I will explain soon. So it gives this infinity functor. So this is nicer than this Gromov-Witten invariant. You know, Gromov-Witten invariant. So I mean, even if you have this Lagrangian correspondence, then quantum cohomology is not it does not induce this ring homomorphism, but Freire homology is, and so this is one reason, and then so why this is open closed map? So if you want to understand this, why this ring homomorphism, quantum cohomology is not functorial. So I want to relate this infinity category, I will explain soon, to this quantum cohomology of X. And there is an obvious relation, which is another main thing. The detail I will explain later, but so the main thing is that there is something called the closed open map. that CO, let me write it Q. Q is a map from the quantum cohomology to this Hochschild cohomology of infinity category. So I'll explain what is Hochschild cohomology, but you have this map. And what's nice is that this is ring homomorphism. And also, this is actually L infinity homomorphism. And it is expected to be an isomorphism in many important cases. Then you can think the following things. So then we have another thing, open closed map. And it goes to the dual, something called the Hochschild homology, which I'll explain later, of this category of homology of X. And this is actually the module homomorphism over this ring. You mean that homology of X is a module over cohomology of X, right? You have a cap product. And actually, this L infinity structure here on the cohomology of X is actually a trivial L infinity structure. It means that all the operations is 0. And this one has something called a Gersten-Haber bracket. And also, this is a kind of L infinity module homomorphism. So now, let me mention the following things. Suppose you have this infinity functor. So you have to write it out there. So suppose you have this infinity functor in general. So this is infinity functor. If you do not know infinity functor, you can think for a while it's a kind of ring homomorphism. If you have a two ring and you have a ring homomorphism, then what is known is that if you take this Hochschild cohomology, is not functorial. If you have a ring homomorphism, you cannot define this morphism between Hochschild cohomology. That's rather easy because Hochschild cohomology is something like some tensor product of X to the, so you have a ring. The Hochschild homology of A is just something like a hom e to the tensor N A, and you take some Hochschild differential. And you say that this domain is domain and target is mapped by homomorphism, but it is contravariant in the domain and covariant in the target. So there is no way, no natural way, so that you have a ring homomorphism from HA to HB. It induces a homomorphism between Hochschild cohomology. However, it is very easy to see that the Hochschild homology, so this W induces a homomorphism of the Hochschild homology on an infinity functor on this category. Because basically Hochschild homology is something like it's a bit imprecise, but something like you take the sum of the A tensor K plus 1, and you have this Hochschild differential, right? So this is obviously covariant. So if you take the Hochschild homology, it is covariant. So now the statement I just want to put in the title is the following conjecture. Conjecture is the following. So you have this Lagrangian correspondence. Then we consider the following diagram. So we take Hochschild homology of the infinity category associated to X1. And you have this infinity functor, W. So W is the name of Wilhelm and Woodworth, maybe Weinstein, who construct this kind of functors. By this functors, it gives this homomorphism to Hochschild homology of X2. Then we have this open closed map to the homology of X1. And then you have a natural map, X2, and you have an open closed map. And this map should be, this diagram should commute. So what is the horizontal map? This is very easy. So you have this cycle in X1. Then you take this Q cross X2. Then you take intersections of L1, 2. Then make it transversal then this quotient 2. So this is something like a very natural map which this correspondence associate to homology group. And the conjecture is that this so W12 is something like commute with this Hochschild open closed map. And so I still do not understand how this related to this non-functoriality of quantum cohomology, because suppose that this is true, then this Hochschild homology is actually functorial, and also open closed map is functorial, and one can say that Hochschild cohomology is dual to Hochschild homology. So if you take this dual here, so this is basically the dual, and in many cases we can actually prove this open closed map and closed open map is an isomorphism. So we have this functoriality, and also as we say that the closed open map fits and also closed open map Q is dual to open closed map. So if you put everything dual, then you get this map between this, you have this map from the quantum cohomology to Hochschild cohomology, and quantum cohomology to Hochschild cohomology. So everything is dual. So you may wonder why this commutativity does not mean this functoriality of the Hochschild cohomology. It means that the quantum cohomology should be ring homomorphism. And the reason is very easy, because this duality uses the Poincare dual. It's not usual duality, it uses the Poincare dual. And of course, this Lagrange correspondence may have a different between spaces with different dimensions. So basically, quantum cohomology is not functorial because of this rather delicate non-functoriality of Hochschild cohomology and this duality between homology and cohomology. So that is this problems. And so this is the conjecture. So the main statement I want to make today is some weak version of this conjecture. So this is the theorem. This is a work in progress, because I wrote some papers, but I didn't finish it. It's the following. So we take these situations, Hochschild homology of the category, and Hochschild homology of the second category. And then we have a map to the homology of X2, but you can identify this cohomology by Poincare duality. And then you have this map from this cohomology of X1. And this is something like a Gisin map. Then you compose it with a closed open map. Then you get Hochschild cohomology of Fx2. And the theorem is that this diagram commutes. So it doesn't, I cannot yet prove that this one is proved, but you compose it from the closed open map and to land with in this Hochschild cohomology, then we have commutativity. And this is not so bad because in many cases, we can show that this Q star is actually an isomorphism. In some cases, there's something called the generating criteria holds. This open closed and closed open map is an isomorphism. So in that case, we can prove this conjecture. So that is the theorem I want to in the titles. So, but I want to explain more about this about the constructions of everything. And so now this is theorems, and probably I hope I can come back to these theorems at the end of my talk. But before, I want to explain how all these things are constructed. And actually, so many part of these things we are constructing with this paper with our full. So A is Abuzai. And 3O is Yongin O, Hiroshi Ota, and Kaoru Ono. And F is myself. And there is a paper which we announced actually more than 10 years ago. And you can see in a reference in our papers, there is a paper called our full paper. And we almost finished writing it 5 years ago, just before a pandemic starts. And then we found some small gap in the proof. I don't want to explain that point, but and also there are one sign issue. Sign in infinity business is extremely complicated, and those 2 points are not so. Then we stop for a while, and now I think we understand these points, so everything should be okay. But anyway, And most of the thing I want to explain is in this paper. And unfortunately, not yet finished, but I want to finish it in a few words. So what was this MVT category? Associated to simplex manifold X. So the construction of this MVT category is also rather heavy work. And maybe in these 10 years, maybe we wrote many other papers and it makes it more transparent. But anyway, we need to start with some set, L1. This is a finite set of something called a relatively spin, a Lagrangian submanifold of X1. Maybe let me assume that X1 is a compact symplectic manifold. And you do not want to see what I mean relative spin, so you may just assume X is spin and this submanifold is spin also. But anyway, so now then we associate L1 something like a infinity category. So that its object is a pair of LB, and L in X is a compact Lagrangian submanifold. No. This L is an element of this finite set. And B is something called a bounding chain. It's rather long story to explain what it is, but basically B is an element of odd degree cohomology of L with something called a Novikov ring coefficients. I will explain what it is, and it satisfies something called the Molar-Cartan equations. It's something like a lambda times 1. Maybe let me write it E. So what it is, so first of all, what lambda 0 is a ring. Pardon? That's what I will soon explain. I want to explain these three integrants, one to one, the other. So lambda 0 is a ring, which consists of the infinite power series, k, t to the power lambda k. This lambda is a bit, let me write C. So what is this ak? Ak is a real number or complex number. Maybe today I want to use real number, for example, but maybe complex number. And lambda k is a real number, but it's positive. And it is increasing up to infinity. So you have this infinity. So this is a ring, and you can have obvious ring structure. And mk is an operation which goes to from maybe cohomology of L tensor K to cohomology of L. So everything is this lambda 0 coefficients. And I don't want to explain in detail what it is, but it is basically the following things. You have this pi, its cycle. Then mk, p1, blah, 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 pk, its coefficient of p0 count these disks, holomorphic disks. So that it looks something like this. So suppose you have this P0, P1, P2. Then you take this holomorphic disk, which intersects P0, P1, P2 at the boundary. This is P0. Right? So U is a map from disk with boundary to XL1, XL, so that U is holomorphic, so D bar U is 0. And this weight is t to the power on this integral of symplectic form. And we need to write several hundred or maybe 1,000 pages to make this sense, to have a well-defined meaning of this moduli space of holomorphic disks, and to have some kind of intersection theory, and to systematically perturb everything, so that in total it gives a well-defined map like this. So that's a long story, and I don't want to talk about it. But then we have this MK, series of operators, and B is satisfied these equations. And so you can see that this equation, so in the case, simplest case, C is 0. This equation is just MK, BBB is 0. And easy case, in the easiest case, that M1 is some drum differential, and M2 is a wedge, and other MK is 0. Then this equation is just dB plus B, wedge B is 0, and maybe B is a one form. This means that D plus B is a flat connections. And this is originally called the Polar-Cartan equations. And this is something like a generalization of that equations. And but you have this C of E. So what is C of E? So E is H0 L lambda. This is a so-called unit. It's just represented by differential 0 form 1. And you have some number C. C is lambda 0. So this is some weaker version of the Polar-Cartan equation. You have this something related to this special value. That's called the potential values. So this is basically the object. So object is a Lagrangian submanifold plus bounding cochain, which is a solution of this. So object of the category, maybe write it L1. So L1 is associated to this L1. This is just a pair of LB, and L is an element of this Lagrangian, the leading bounding cochain. And there is some technical reasons we need to restrict to this finite set. I mean, it would be nice if you can just take all the Lagrangian submanifold as an object, because this is most natural. But then the construction had some trouble. We use some inductive limit process, so that the inductive limit should have some nice property. And if you take all the Lagrangians that are a bit too huge, and we don't know how to work out that in that kind of situations. So we just restricted to finite set of Lagrangian submanifold, but any finite set. Okay, so now what is the morphism? But the morphism, no, we have morphism, so this is called the infinity category. So what it means that, so let me write it B, K, L, C, C prime. So C, C prime is a object. And the morphism is a vector space. So morphism from C1 to C2 is free, no, not free. No, free lambda 0 module. And for various reasons, I want to take it finitely generated. And in this case is this guy. So if this C1 is L1 B1, C2 and L2 B2, then I want to assume some kind of transversality. And in this case, it's this morphism space. It's just the usual homology of L1 intersection L2. So if the intersection is L1 is not equal to L2, the transversality means that it is just finitely many points, a finite lambda 0 module. And if it is if L1 is equal to L0, L2, for example, then you have some L itself, and you take the homology of L itself over real, and lambda 0 is over real. So it contains real numbers. So this is a real homology group tensor with lambda 0. Lambda 0 is free real module. So this is situations. And infinity relation. So we take this big, so this is a module, and we take this BK, L, CC prime. So that is sum over all this C0, blah, 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 CK on this tensor product of L, Ci plus 1, And this C0 is C, and this CK plus 1 is C prime. So you take this, all this K tuple, which starts from C1 and end up with CK, C prime. It is just sum. So you have this guy. So this is something called a bar complex. And MK is an operations, which goes from BK, L, CC prime to L, CC prime. So it's just one operations for each K. And what we can, so then we assume that this sum of I plus J is K, Mi, blah, 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 Mj, blah, 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 it's 0. You have some sign. So this is called the infinity relations. And Mk is defined in a very similar way as before. So if this L0 is L1, blah, 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 Lk are all different, then Mk is obtained by counting polygons, which is something like this. So basically, if you see this, that this guy is a finite dimensional lambda 0 module whose generator is the intersection point. So you count this. So for each, so this is something like a P1, P2, P3, P4, P5, P0, and P1 is, for example, L, C0, C1, or blah blah blah. And then you count this kind of polygons with weight t to the power of the areas. And that is this operator Mk. And the main equation is that if you repeat this Mk twice, you get this infinity relations. So this is an infinity category. And the final form of this construction, at least one real coefficient, is the following. So this is, I think, written in our book, which should appear. This guy, so this L, one which is cyclic and unital infinity, filtered infinity category. Infinity category, and which is independent on the choices. It depends on the finite set of Lagrangian sum manifold, of course, but independent to anything else. And the cyclic and unital plays a role in these talks. I want to explain what it is. So what is cyclic? So what is unital? Unital means the following thing. So you take this morphism space of the same Lagrangians, and unital means that this guy should contain some E. This is a unit. So that M2 E X M2 XE and X. This is X. So this is, you can easily see the E's unit. And then MK blah 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 E blah 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 is 0 in all other cases. So this is called the exact unit. I mean, so you know that for the axiom of category come with very small number of axioms, and existence the unit is one of those few axioms. So it is important in some sense. But in our generality of this cyclic manifold and finitely many Lagrangian sum manifold, to cook up this exact unit is actually some non-trivial business, and we finally do it in this book, in this paper, and so this is the unitarity. And the second thing is cyclic. So infinity category is called cyclic if you have some pairing between L, CC prime, and L, C prime C to this ground ring, such that if you take this X0, MK, X1, XK, then, so you take this guy and take inline product X. So this is something like a plus minus with X1, MK, X2, XK, X0 up to sign. And this sign is something called a Koszul sign. And then this one is non-degenerate in a product. In a finite dimensional setting, this is actually non-degenerate. So what is so this is the second theorem. And if you know something about this theory and Lagrangian things, there is some notion called the Calabi-Yau property. And if you know something about algebraic geometry, then if you consider the category of shifts on a manifold, then this is something called the cell duality. But of course, in cell duality, you need something called the in cell duality, this homology of E and E prime is isomorphic to homology of I forgot. Homology of E is isomorphic to this homology of. When you dualize, you need this K, right? So for example, yeah, I think this is correct, right? Something like this, right? You need to use this structure C. Maybe only one side. I forgot, yeah. and in the case of this Calabi-Yau manifold, Calabi-Yau manifold is by definition that this canonical CF is trivial. So this is a kind of very canonical, just E and E prime extension of E and E prime is isomorphic to E prime and E. That's called the Calabi-Yau property. And the Calabi-Yau property, you can define Calabi-Yau property on this MPT category also. But the difference is that this equality is a bit stronger than Calabi-Yau property. And Calabi-Yau property basically means that this kind of equality falls up to J homotopy. So Calabi-Yau is something like a more kind of homology level conditions. And I think there is a theorem which is announced by Kontsevich and Soiberman that Calabi-Yau property implies this cyclicity. But it works in under certain assumptions, which is not in general satisfied in our particular situations. But we could prove this kind of honestly by geometry. And to realize this unitarity and cyclicity at the same time is some technical problems, and which actually takes 5 years for us to complete. So I don't want to talk about it, but to make this two property rigorously is somewhat non-trivial. And you can see that what is unit in this case is unit is just in our situations of this L. Unit is something like contained in this H0 of L, and this is just one. You have a very canonical unit, and you try to do this. Then this one is a fundamental, basically a fundamental class. In fundamental homology class, and its homology class is 0. It is very natural if everything works fine that this holds, but we need to make all the perturbations synthetic. And cyclicity, so this inner product, in our case, inner product is something like a homology of L1 cap L2 and the homology of L2 cap L1 goes to lambda 0. So in the case L1 is transversal to L2, then this is something like L1 equal to this is equal to L2 plus L1. So you have natural pairing. And in a case when this L1 and L2 are equal to L, it is the same. Then this is something like lambda is just a Poincare duality. Right? So you have this kind of inner product, and if you look this definition of MK a bit carefully, then you see everything is kind of cyclically symmetric, and this cyclic symmetry in principle is obvious. But what's different from in principle and actually is that you need a lot of perturbations or something to make it works, and to make all of this is compatible with this is somewhat non-trivial. So this is about the infinity category. So I next want to say what is the open-closed map and closed-open map. But before, I want to explain what is Hoshi homology and Hoshi cohomology. So I want to define Hoshi complex, of some infinity category. So it is sum over L, C0, C1, tensor B, K, reduce C1, C0. So maybe L reduce CC bar prime is just LCC prime. If C is different from CC prime, and it is L, CC prime divided by this unit. This is the usual terminology of reduced things. You can just kill limit, kill unit only from the second to the last factor. And C0, C1, C1 to C0. This means that so the element is just element is something like a start x0, tensor x1, blah blah blah, xk, and so x0 is from C0 to C1, blah blah blah, xi from Ci to Ci plus 1, but xk starts from ck but going back to C0. Right? It is this Hochschild complex. So this is the Hochschild chain complex. And the boundary is so Hochschild boundary from x0 tensor x is a sum over x3, 3, m, x3, 3, x0, x3, 1, tensor x3, 2. I'll explain what it is. Plus, I forgot all signs, so I just do it. x0 tensor x3, 1 tensor m x3, 2 tensor x3, 3. So what it is, so you take this x, and this is x1, xn. So you take this, let me write it C. And then we take this twice of this co-algebra structures. This is something like from x1, blah 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 to xi, tensor xi plus 1, blah 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 xj, and xj plus 1, blah 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 xk. So you take this all possible way to divide from x1 to xn into 3 parts, and it is a sum of this. So this is a x3 1c, and this is x3 2c. And this is x3 3c. So you take this. So you first divide this differential so that the x0 is contained in the part you apply your operations, and then this is something cyclically symmetric. You put here and x3 3, x0, and x3 1. You apply m, and the rest is here. The other part is that you don't apply m to x0, so you just apply this arbitrary part. This is the second part. So this is called the Hochschild differential, and it is a kind of easy consequence of MPT formula that this square is 0. So you have this Hochschild homology. So Hochschild cohomology is somewhat very easy, simple, similar. So Hochschild cohomology is the following. So we take this Hochschild cochain complex of L. It's just a sum of all of this hom be reduced L CC prime and L CC prime. So this is the Hochschild cohomology. I mean, so this one before is a kind of tensor here. So you just move this to the domain part. And the Hochschild differential maybe it's better because this time is coming closer. So I just do not define what is the differential, but it's very similar to Hochschild homology. So you have this Hochschild cohomology using this guy. So the next thing is about so for this I think so there is actually for Hoshid homology and cohomology there is a reduced version and non-reduced versions. I mean, so other than the one component, reduced version just you kill all this unit. And to make it possible, you need unit in a strong sense. It's a kind of exact unit. So that's somehow play the role. And then what I want to say, so what is Q, close-up map? So you have this, so suppose you have this, maybe simply you have this thing, then you want to have a map to this home. So this is something the following. So you have this things. So maybe let me consider this all C's. All C is just L. I mean there are cases that there are KC, different C, but for simplicity you just want to consider only one Lagrangian. So now what is this map? So input is the following thing. So you have some input H. It's a differential form of the ambient space. And you have this x1, blah, 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 to xk. Is a differential form, say, I mean, you are taking homology of L. Then this Q, H, x1, blah, 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 xk should be the differential form on L. So how to do it? So you take this H here, and you put the x1, blah, 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 xk here. So you take this moduli space. Moduli space, U, so U under this x1, blah, 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 z1, zk. And U is a map just with boundary to xl. And zi is a point of boundary d2, and all are different, and all are not 1. And zi respect cyclic ordering of boundary D2. Then, so this is the moduli space, which I want to call M. I'll draw this picture again. So you have this, so this is the kind of M, K plus 1, 1. So K plus 1 means the following. So you take this 1 as a marked point. So Z1, blah, 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 ZK. And 1 is something like another marked point 0, so it's the interior of D2. So you have this D2. You have this 1 here, and Z1 here, Z2 here, blah, 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 ZK. And you have this 0. And why this is simplified, since we take this 0 and 1, it's a marked point. So this which fixes these 2 points is actually trivial. So this is a moduli space is easier because there is no automorphism. So this is a moduli space. And then what you do is the following thing. So you have this moduli space, mk plus 1, 1, and maybe homology class of U is beta. Then you take this map from this LK cross X, and you have this L. What is this? So you move this U to this UZ1, UZK, and U0. And this one is U1. So you have a map from here, U, to XL. Then you can take a value from this Z1 to ZK. So this guy is an element of L. So you have a K point of L. And you take the value at 0, it is another element of X. And you take this 1, you have another element of Y. So now, this guy is basically the following thing. So let me write it Fs. And this is Ft. So this is first this, you take this H, but you take this X1, blah, 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 Xk, times H, and you take this S star. So you have a differential form on Lk plus X. It is this X1 to Xk, which is the differential form on L, and the H, which is the differential form of the ambient space. You pull back, and then you push out. So that is the differential form on L. So that is basically this closed open map. And this is, I wrote it in the differential form, but it is basically count this kind of configurations. So this is called the closed open map. And and one need to show that this is actually a chain map. So this gives the chain map from the differential form on X to this Hochschild chain complex, or chain complex of this category, and this is a kind of chain map. That's another thing I need to prove. And something else I claimed is that this chain map is not only a chain map, but it is a ring homomorphism. Ring homomorphism means that you put this quantum cup product on a domain, it's a cohomology of X. It's so-called quantum cup product. On the target, you have Hochschild cohomology, and Hochschild cohomology has a kind of product which is another called a cup product. So this is a ring homomorphism. So this is Q, and P is, so I don't want to talk so much because then I don't have enough time to explain. So P is something like this. So in this kind of story, there is something called the input and something output. Here, so you know that these are input, and you pull back and you push out at some point. That's the output. And in this case, input, so including this interior mark points, they correspond to input, and only one point in a boundary is output. So that is a closed open map. And in open closed maps, everything on a boundary is actually input, and output is interior. So you use basically the same modular space, and you just change the role of input and output. You take this P, so P is a following. It's called from the Hochschild chain complex of L to the cohomology of X. So this is a closed open map. No, this is Q is a closed open map, sorry. And this is open closed map. I mean, open means that this Lagrange-Freya theory is something like open part of the story. And closed means that Gromov-Witten theory is a kind of closed part. So this is Gromov-Witten theory to Freya homology. This is a map from Freya homology to Gromov-Witten theory. So I don't want to explain the detail of the definitions, but there are several statements. As I said, there are the following statement. So Q is a ring homomorphism. So Q X cap quantum cohomology Y is a Q X cap Y. And the Q is a L infinity homomorphism. And the P is, you have this P, P is a module homomorphism over Q. So what it means that if you take this Q of X cap Y and P is a X cap P of Y. So X is a cohomology class of X, Y is a Hochschild homology class of L. So you take the Q of X, it's a Hochschild homology class, and Hochschild cohomology has an action on the Hochschild homology. That's called the cap product. I don't want to define, but you have some natural notion of cap product of Hochschild cohomology to Hochschild homology. And then you move it to P, then you move it to Y, then this is a homology class and this is a cohomology class, you have a cap product. And also, I don't want to explain precisely that the kind P is L infinity. So now, I want to mention some important property is the following. So there is a inner product on Hochschild homology of L. And this inner product is, I think this in the literature, it is called a square inner product or Mukai pairing. So it's a following things. So suppose that you have this X0, X in a Hochschild chain complex of L and Y0 plus y in a Cauchy chain complex of L. Then the inner product Z is basically something like this. So you have this thing. So you have to put x0, and this is x1, x3, 1. And here you have x3, 2. And this is x3, 3. And this is y0, and this guy. So y3, 1, y3, 2, and y3, 3. And you have some element fg. And you put m. I don't want to write down the formula, but it's something like so you cut this S1 into 3 parts. Then here so you have this intersections on this line and on this line, and you take this all sum and you take all m on this thing. So you can write down the formula, but I think it's just lengthy. It's not so much just illustrating. For example, this formula, this one corresponds to m. x0, x3, 1, f, y3, 2, x2, 3, maybe x0, something like this. This is this part. And you have a similar thing for this part, and you take multiplications and take all sum over fg and all splitting. That's called this z. And the z is kind of known to be a. So now the theorem, which is called the Cardy relation, and it is known in physics something like 30 years ago, is the following. So you take this Poincare pairing of p of x and p of y, and this is equal to this z of xy up to sine. So this is called the Cardy relations. And this has a long history actually in symmetric geometry. There are several people like Albert or Milan Cornea. And after we mentioned it, there are several other people like Shiraka Natura or Sheridan or several other people who study this kind of thing. But probably in the compact case in this generality, maybe it's what we proved. And so this is something like this closed up, open closed map preserves this inner product. And maybe I don't have a time, so I just do not want to say so. But then so probably I mentioned that the main idea of the proof is the following. So we have this configurations, and if you look this, I cannot explain detail, but it looks something like this. Here is x, and here is y. This is open closed map, and this is open closed map you intersect. This is this, and this is this. So then in a moduli space of complex structure of annuli with two marked points, you have just two particular points. So this is something like so this is some two particular point of the moduli space of annuli, and these two are kind of connected in the moduli space of annuli, and you can just use this cobordism to relate these two. So this is called the Cardy relations. And maybe some of the main application of the Cardy relation is the following things. Is the following thing. So suppose that the P is Hochschild homology to L to homology of X hits this 1 in H0. No. Yeah, unit. Then so there are two consequences. Is the following things. If for any u be u, so that Fourier homology is non-trivial. Fourier homology is the homology of M1 of these first operations. over lambda, and then you take this right, and this C, there exists this LB with Frey homology non-zero, so that it's B. This is the same. I don't want to say the detail, but basically it's this category split into various value of this particular value C. That's called a potential value. So it means that once we have enough things to hit a unit, then everything is everything is coming from here. And then another thing is the following things. So suppose any like this. So you take this L plus, it's just L plus this particular U. Then you take this infinity category. So from this L, from one extra element, and this is isomorphism equivalence after changing lambda 0 to lambda. So you invert this generator to have a, so lambda is lambda 0 with the inverse. We make it a field, and take so-called a split closure. Okay, so now this is the kind of most of the things we talked about this structures, and probably it's not a good idea to try to explain the proof of this functoriality of open-closed map. I just want to say a few more things. Some more things. So in our reduced setting, there is some operator B from the Hosh's chain complex of L to Hosh's chain complex itself, which goes to from x0 to unit tensor x0. And this is called the cons operator. And one can easily check that this B and Hosh's differential just commutes. So you take this Hosh's chain complex plus UB. This is a so you take this Hosh's chain complex L tensor lambda 0 maybe for Hosh's U D, and D square is 0. So you have this cohomology with the extra generator U, and the cohomology of this guy is called I think cyclic homology of your manifold. And what one can show, so this is called a cyclic homology. And it is rather easy to show that the lemma is the following: B and the open closed map composition is 0. So for what it implies, so this guy gives some exact sequence called, so the cohomology is called maybe let me write it HC of this cyclic homology, and there is a map is times U Hosh's of L coming back. This is natural exact sequence, and what we can show is the following. We take another exact sequence. You can just take homology of X, and then just take homology of X with this U, and homology of X with this U. Then you can just take A to A times U and just projections, and this is 0. And then what we find is that this is actually isomorphic. You have this P. So this diagram, this is actually a trivial diagram. You can just use trivially and just make it U. And this could be a priori non-trivial. You have this B, And the theorem says that if P is isomorphism, then this actually is an isomorphism. It implies that this exact sequence between cyclic homology and Hodge homology is trivial. And this is called Hodge to Drum degenerations. And it is used by, I think, conjectured by Konsevich and Soberman in some generality. And we can prove it in a situation where there's open closed map is an isomorphism. And that's for in the case there is a generator. And something similar is that if you consider this inner product, then we can prove this kind of things. This is also very easy. So Z induces inner product on this cyclic homology to this lambda U, which extends to this to the Hodge homology things. And if my understanding is correct, this is something related to, so in the mirror symmetry, this extended one is something called a higher residue pairing due to Kyoji cycle, and original Z is a residue pairings. So I think we can cook up most of the structures which is expected in a mirror side from this symplectic side. And also many things are much functorial. For example, cyclic homology is functorial and everything is kind of just commutes. And they say that the functoriality of P is related to that all the structure I just explained is functorial with respect to this Lagrangian correspondence. Okay, so maybe I think I don't have enough time to explain this theorem, but I just stop here. Thank you very much. Yes. I mean, so the condition is that P is unit. And the case we know is that, I mean, the various way to obtain the following things. So I mean, the point is that to find enough Lagrangian submanifold. And so if you have some Lagrangian submanifold, which is as many as a kind of a Betch number, then this is an isomorphism. So that's the way. And we proved it in the toric manifold. And there are several sporadic cases that this kind of thing is proved. Like I think Gelfand charting system, blah, blah, blah. So I don't know, in Fitch generality, it's okay. But the conjecture is that it is true for any projective algebraic variety. I don't know how to, this conjecture, I don't have any idea how to prove it. Yeah, I mean, I call it mirror to Hodge conjecture. So you think it's so difficult. Yeah. Yes, it should be regarded as a different object. It happens, for example, in the case of P2, you take Clifford tori, and on Clifford tori you have three different Vandenko chain, which has a different this value of C. So they are completely different objects. Yeah. So in that case, I mean, it's a bit imprecise. You have L with B and B prime. Then the chain complex is not a homology of L, but homology of L with some local coefficient. Local coefficient is a B minus B prime. B minus B prime is something like so this leading order term is one form. You can put flat bundles.